Well, I'm very happy to be here in FPSAC, and I think I spoke at FPSAC when I was a graduate student, and I visited many times, been in a lot of program committees and organizing committees, but not as involved as other people, but kind of involved enough. So today, I'm going to tell you about something that I've been working on for the past almost 10 years now. It's slow, but we feel that we are making progress or some progress, right? Although it's not full progress yet. But I want to tell you a little bit. And since I remember being a graduate student, I thought I would start the talk, kind of slow. But before that, I want to tell you that this is based on work with Franco Saliola, Anne Schilling, and Mike Zabrocki, who's sitting right here. Franco and Anne are not here this year, sadly. And it is based on two papers that we've written, the Plethysm and the algebra of uniform block permutations, and a more recent, a lattice of summonoids of uniform block permutations containing the symmetric group. I want to thank AIM. These are mathematical institutes in the United States, ISERM, and BIRDS at Banff, because these institutes are amazing in allowing groups of collaborators to go and work there. Like Overwolfach also has something here in Germany. I know some people are collaborating, but we've gone to all those, and it's a wonderful experience because although we meet every week on Zoom, we meet for 1 week in person, and all of a sudden things start to happen again, right? So I'm very grateful for their support. So anyways, so starting with like a very basic slide to set up notation, right? So this talk will be about, symmetric group and general linear group later, right? But, if a representation, right, is just a homomorphism for me as a combinatorialist, that from the symmetric group to the general linear group. If you don't know, if you're in the sad situation that you don't know anything about representation theory, you can fix that. And there is a wonderful book, Sagan's book, that from where I learned almost everything, that is on this slide and more. So the irreducible representations in this talk will be labeled by S lambda. They are indexed by partitions of the number n. As a module, like I'm going to think, since I'm a combinatorialist, I'm going to think about the modules as being just spanned by a standard tableau of shape lambda. And what that means is that they are boxes, right? Like the lambda tells you the shape, and a standard means that you don't repeat numbers. This becomes important later. The character is the trace of the matrix that you obtain. So just the trace. And so here I gave you an example of how the character tables, if you have never seen them. And basically what this records is the trace for each of the matrix representations, right? And there is one for conjugacy class. So the columns here are conjugacy class. This is important later. So restriction of so in this lecture, I'm going to be interested mainly in restricting representations, which sounds kind of simple enough. Like, you have a representation of your whole group, but now instead of acting by the whole group, you just act by a subgroup, right? And in general, that will not be irreducible anymore, and it will decompose into irreducibles, and basically you want to figure out what those numbers are, right? And if you do it for the symmetric group, here is an example, and you want to know, like, here if k is equal to 6, m is equal to 5, right? And so you take a partition of 6, a partition of 5. You know that this representation of this group, like, this direct product of groups, occurs 3 times. times in the representation 5321 for the symmetric group S11. And there is a very beautiful, combinatorial interpretation for those coefficients, right, in terms of some tableau that I'm not going to tell you because it's not relevant for the talk. But, like the multiplicity, that multiplicity for this data, right, is given by, counting a set of tableau, right? And when I say combinatorial interpretation in this lecture, I mean something like that. Can I find a set of tableau where I do some, thing with the boxes, right? Some boxes might be left empty, right? And if I count those, that's my combinatorial interpretation. So we move to the general linear group. The general linear group for this lecture is just going to be n-by-n invertible matrices, or if you like, you can think in terms of linear transformations. We have the same situation, but now you're representing, an n-by-n matrix with an m-by-n matrix. And for the purposes of this talk, all the representations that I'm going to be interested are going to be polynomial, in the sense that, when you map a matrix to another matrix, all the entries are going to be polynomials on the original matrix, right? So this is an example, right? Like the irreducible polynomial representations are indexed by partitions again, but now they have at most n parts. For the symmetric group, they had exactly n boxes, and now they can have at most n parts. They can have fewer parts, right? So I'm going to use V lambda as the module, and in contrast with a symmetric group where you had a standard tableau, now you have semi-standard tableau. And a semi-standard tableau allows repetitions of the numbers, like, it's not a standard anymore, it's semi-standard, but the numbers have to increase weekly along the rows and strictly on the columns. And here is just to give you an example that the same partition can represent a representation for all different groups. And all that matters is, when you construct the bases, up to what number do you use to fill the boxes? So here you use from 1 to 2, and if you're in GL3, you will fill with 1 to 3, and so it gets bigger depending on what GLN you're talking about. And if you have any questions, please speak up, because yesterday I saw some people raising hand, but the speaker was looking at the slides and couldn't see. So please feel free to interrupt me at any point. So more about the general linear group. So the characters we saw for the symmetric group, we could put them on a table, right? But for the general linear group, since it's an infinite group, you cannot put them on a table anymore. So, but they have a very beautiful structure. Like they are actually evaluations, which I'll explain here in an example, of Sure functions or Sure polynomials, if you like. A Sure function is a symmetric function. I'm not going to define very much except this. And this is the generating function. So here, x can be any set of variables. It's just kind of a stand-in. And the idea is that you take semi-standard Young tableau, and what does this mean? It means that you have tableaus where you can have repetitions, just as I described about in the previous slide, where the numbers increase weekly on the rows and strictly on the columns. That's what this means. The lambda tells you the shape of the tableau, right? Like how many boxes you have on each row. And then you sum all the monomials that you can find by filling out the numbers with numbers from 1 up through n for GLN. And you will get a polynomial that happens to be symmetric, which is the same that Arun described yesterday in his first slide, the Sure function, right? So for instance, for GL2, right, very simple example, like you have 3 monomials because there are 3 tableaux, right? And 1 for each tableau. So if you wanted to compute the characters of elements, right, you would find the matrix, find the eigenvalues, and plug those eigenvalues into the Sure function, and you will get a number, and that number is the character, the trace of the representation. Okay, and there is a very beautiful correspondence, right, between polynomial representations and symmetric functions. And you have, so here is a table, right, of how the characters correspond, the irreducibles to Schur functions, the symmetric tensors to homogeneous, the alternating powers to elementary, and if you take tensor products in general, right, like they correspond to products of symmetric functions. These numbers are the same Littlewood-Richardson coefficients that perhaps some of you recognize when we did the restrictions of the symmetric group representations because they are in duality. So there is a duality, those numbers that are occurring. So anyways, so what is Plethysm? So in the title, right, I had the word Plethysm, and it's very simple to define for, in terms of the general linear group. There is also a definition that uses the symmetric group, but I'm not going to use this one today. So you have two representations, right, of the one for GLN, and it maps, n by n matrices to m by m matrices, and then you have a representation of GLM that maps m by m matrices to r by r matrices. So the composition of the representations, right, is going to be a representation of GLN because you go from GLN to GLM and then to GLR, right? And then this composition, right, is what people call Plethysm when you are talking about symmetric functions, and we will use the notation F bracket G to denote the Plethysm of the characters. And here is a simple example of how it works, right? So we saw in the previous talk that S2, X1, comma X2, right, is a character of GL2, and because you have these three tableaus, but if you increase it to one more variable, you will have, 6 tableaux, right, and you will have 6 monomials like that. So if you wanted to do the Plethysm of S2 with S2, now you have to, your variables now become the monomials that occurred in this expression, and monomials with multiplicity. So if you had a multiplicity, you put that as another variable. So you could have repeated variables, right? So now you're going to plug in this, now this x1 squared, right, is going to be your first variable. X1 times x2 is your second variable, and x2 x squared becomes your third variable, and it has become increasingly popular to use this tableau of tableau notion, right? Where now, because of these two out here, you have 2 boxes, right? But now you are entering x1, x squared, which you can represent by 1, 1, right? Or you can enter 1, 2, right? To represent x1, x2, or x2 squared represented by 2, 2, and you have 6 tableaux because of the S2, like right here, but now you get this 6 monomials, right? And the ones that are color green correspond to the monomials that you would get from S4, X1, X2, and the one that is color red, or one of the 1, 2, right, corresponds to 2, 2, X1, X2. And the job of Plethysm is that if you're given any S lambda and any S mu, you want to write it as a linear combination of, in terms of the irreducibles or the Schur functions. So that's the main problem, right? Find a combinatorial interpretation of the coefficients, right, that occurs when you do the Plethysm of 2 Schur functions. And this is a very hard problem. Very few special cases are known, like in generality. For Carré and Leclerc did the special case when the outside partition happens to be a partition of 2 in terms of domino tableau, very nice. In our paper with Colmenarejo and the 3 Saliola, Schilling, and Zabrocki, we look at the case when the inner partition is just M, and the outer partition can be any partition of 3. And this I'm talking combinatorial interpretations that tells you is counting the number of tableaux that do this, right? Or is counting the number of things. How, on the other hand, has given an expression for S4SM, but this uses like some very complicated formulas that get out of hand. So it's not considered a combinatorial interpretation. I mean, if you just even try to read it, it's a very complicated formula. So although it's not a combinatorial formula that tells you the number of objects that do this, right? It's still like, something because you can get some information, right? Littlewood in the 1950s, but you can find them in McDonald's book in page 138, gives expressions for this, which all can be expressed in terms of even tableau or threshold tableau, which I'm not going to give the details because are not important. Beyond that, people have looked at stable coefficients. So if you want to know about this, Chris Bowman is here, and he has worked with Paget and Wildon, and has found some stable coefficients of the stable coefficients in the case SN, SMO, and I wrote it in SAGE notation. So those should be partitions. But even solving this in general, right? Like the special case when the inner and the outer partition are just one row, will solve one of the very well-studied conjecture, which is the false conjecture, that tells you that when you subtract this symmetric function from this symmetric function, you will get something that has only positive coefficients. That's what it means to be sure positive, right? So that means that this would be a representation itself of GLN2, right? Like the difference of these two representations. So it's a very famous problem. In this lecture, I'm interested in the plethysm of S lambda with SM. That's the case that turns out. Yes?
Is there an intuition for false conjecture, like why it's possible?
Well, yeah. An intuition, I would say, intuition is something that comes after you've done like a lot of examples. And after having done a lot of examples, I can tell you that when you are computing like the plethysm, when the n, the outer, is bigger than this one, you will actually get a lot more tableau. So you get a lot more, and this one restricts the tableau that you end up getting, right? So in some sense, since you're getting more tableau on one and fewer tableau on the other one, you expect that this could potentially be true. There are other maybe intuition. If you work with a symmetric group definition, right? You can define vector spaces that are modules that are associated with these ones, and is trying to, basically the idea is to try to prove that one vector space is contained in the other vector space, right? But yes.
Simply, if you evaluate that the identity of the group that's positive, that is a positive expression.
Right. Thank you. Yes. Anyways, yeah, so but this is a very famous conjecture, right? And which tells you the state of things, right? Like that, you cannot prove something, and it boils down to, boxes fitting in one box and boxes fitting in another bigger box, right? Partitions, right, that fit in one type of box versus partitions that fit on another box. But anyways, so our approach with Mike, when we started working on this, we actually were working on another problem that is very hard. And you will understand in a second why this problem is very hard, which wasn't clear at least to me, when I first started to look at this. And this is the restriction problem, right? And the idea is that here you have n by n matrices, right? And you think of Sn as the group of permutation n by n matrices. And this is, as a group, is a faithful representation, 1-to-1, right? So it's a copy of Sn that lives in the general linear group. There are other embeddings of the symmetric group into that have been used by King and collaborators, right? But this is in terms of permutation matrices, and I'm going to think about it like this to kind of be suggestive because of the diagrams that I will be drawing, right? That Sn is contained in GLN, and the idea is that I can actually ask, if you give me an irreducible polynomial representation of the general linear group, What are the coefficients that occur when you decompose it, when you only, act with the permutation matrices on that module, right? What are these numbers that are occurring? We know from representation theory that they are positive. Is there a combinatorial interpretation for this? And here is an example, right, done by Sage. You take just the V2 that I gave you, and you restricted, you are in SL4, GL4, right? S4, and it decomposes like this, and here the coefficients 2, 2, and 1, right? These are the way that it decomposes. This has been studied since the 1950s by Littlewood, by Butler and King. More recently, there is a very nice paper by Narayan, Paul, Prasad, and Srivastava. Paul and Prasad are here, so if you want to hear about it, you can talk to them. And what they did is they proved some special cases of hooks. When the trivial representation, what is but as you can see, very small cases, right? Indicating that, well, this is a hard problem. But how would you do some computations if you, for instance, were interested in working with this, right? The way that you would do it, right? Well, you know how to compute the characters, right? So you can do it at the character level, right? And for instance, let's say I want to restrict this representation from GL3 to S3, and I want to know what the decomposition is. So I would write the character, right? Then I would write the matrices representing each conjugacy class, right, in the symmetric group. So this is the identity, the 2-cycle, and the 3-cycle. Then I compute the eigenvalues, right? So these are the eigenvalues. This is a primitive root of unity, third root of unity, right, for the third cycle. And then if you evaluate them, you're going to get the 6, 2, 0, right? Those are the representation here is of degree 6, of 6 by 6 matrices. So then what you would do, right? Now here you have your character table for S3, and you want to write that character that you got, right, as a linear combination of the irreducible ones, right? That's basically what is going on. And then you find out that the coefficients are 2. The trivial occurs with coefficient 2, and the one with 2, 1 occurs with coefficient 2. So but then this gets very old. So what we did with Mike, which was like a very fun project, we actually formalized it because we thought, well, since we are getting that the Schur functions are evaluating in terms of irreducible characters, right, of the symmetric group, there must be a symmetric function, right, that evaluates, that when you evaluate at roots of unity, which are the eigenvalues of the symmetric group, right? They give you the irreducible characters, right, at some conjugacy class, right? And basically, this project with Mike, right, we were able to find, a definition for these symmetric functions. They are not homogeneous anymore, right? And here are, for instance, if you wanted to compute the character table for S3, these are the 3 symmetric functions that you would have. These are the same 3 representatives, the same eigenvalues. So for instance, notice that when I take 1, right, because you remove the top row here. And when you evaluate them, you get 2, 0, and -1, which is exactly the character there. So we defined these ones, and this allowed us to write, write the restriction problem mainly using symmetric functions, right? So now you can express the Schur functions in terms of these tildes, which evaluate to the irreducible characters of the symmetric group. So that was kind of like a lot of fun, and we got a lot of. So a lot of times, the problems is not about just solving the problem, but the path where it takes you, and where this took us is in introducing a lot of new stuff, like kind of like multi-set tableau, set tableau to do representation theory and things like that. And for instance, if you take the homogeneous symmetric functions, this is kind of a very beautiful theorem that we got, and we obtained a lot of results like this. This is the character of the symmetric tensors, right? And if you want to decompose it in terms of Schur function, symmetric group representations, the coefficients, right, the multiplicities turn out to be the number of semi-standard multiset field tableau of shape, this shape right here, where you do the skewing. So basically your tableaus look like this, right? The mu tells you how many ones, how many twos you're gonna have, right? Like the parts. And then you fill it out in all possible ways. And then you simply record the part without the bottom row. Like you just ignore the bottom row. And for instance, the trivial, right, occurs 4 times, because after you remove, you end up with nothing. That is the trivial. Then you get 7, because you get 7 right here. So, but we got like beautiful results. I just wanted to show you this. The talk is not about this, but like all these beautiful results that counted. We did the elementary symmetric functions, other relationships, and it brought a lot of different things that we didn't know together. And it was like a very fun, but like we were somehow missing something in terms of trying to find, the restriction coefficients, which is what we were after, okay? So, and perhaps this, to the people that know, perhaps this should remind you of the Koska. So this would be the Koska for when you allow multisets. Like it's exactly Koska, but now you are allowing entering multisets in the tableau, okay? So anyways, so how does Plethysm relate to restriction? Because, if you solve some special case of Plethysm, you will get restriction, right? This is the problem that we are looking at. And in 1950, Littlewood was working on this, right? And this was put into modern notation by Scharf and Thibon, who had a very nice article, and says that these restriction coefficients, right, are obtained by taking this Plethysm, right, where you are actually taking, so this, the way that you should think when you see these pluses in the literature is that you're taking all the variables that occurred in S1, which is x1, x2, x3, right? You put 1 is one of the variables. If you have S2, you will have all possible degree 2 monomials. If you take S3, you have all possible degree 3 monomials, etc., right? And you look at the coefficient of S lambda that occurs in this Plethysm, and that would be the restriction coefficient. So here, S lambda Sm, right? If I were to solve the sub-problem that I'm interested in, this would actually solve the restriction problem, right? Like, so that's how they relate. So the next thing on my talks were seesaws, right? And what is a seesaw pair, right? So you will have a seesaw, right? You have 4 algebras or 4 groups. And it so happens that B1 is a subgroup of A1 or a subalgebra. You have B2 is a subgroup of A2, right? So put in this notation, these are the seesaws, right? Like the crosses. And you have a vector space, which is a module, actually. So you have all these 4 groups or 4 algebras are acting on the same vector space, right? And you have this relationship that A1 and B2, right, A1 and B2 are centralizers of each other, right? So how do you read this if you are kind of, you're basically looking for all the linear transformations that commute with the action of A1 when it acts on W, and those are just the elements in B2, right? So that's how you read this. So these are kind of commuting, right? The actions commute. That's the way that you can think. So they form centralizer pairs if these 2 conditions are satisfied. And what the seesaw relation tells you is that if you restrict from A1 to B1, if you restrict representations on this side, you will obtain the same coefficients as if you restrict from A2 to B2. Like, that's the general result. The same coefficients, although you are adding over, a different, I have a typo, but it's corrected in the other slide. But you get the same coefficients occurring, the same multiplicities. So you can transfer the problem to another pair of groups. That's kind of the idea. So here is our seesaw, or what we have so far, right? So we know by Schur-Weyl duality, the GLN, right, acting diagonally on V tensor K, commutes with the action of the permutation action of Sk on the tensors, right? It just permutes the positions of the tensors. So that is from Schur-Weyl duality. And here we know that Sn is contained in GLN, this containment that I was telling you. And then basically, what commutes with the diagonal action of Sn, right? On V tensor K. So what is the commuting? So what we are asking is that if I allow Sn to act diagonally, right, on tensor product, what will commute? And the idea, I cannot go into much detail because is they are going to be linear transformations. So this is going to be some sort of linear transformation. And the linear transformation is going to correspond to a set partition. The combinatorial data is a set partition. Here is, so in general, right, that question mark in that seesaw diagram, right, is what is known as the partition algebra, which is a diagram algebra, which you saw yesterday in Jean Scott's talk, right? She was talking about diagram algebra, so in the same sense here, the same idea, right? Basically, the basis is going to be combinatorially simply set partitions. So if you give me a set partition, this is a set partition of 8, the set with 8 elements union with, some bar set of 8 units. And the idea here is that you're putting the bar numbers on top and the bar numbers on the bottom like that, like very similar to what Jean was doing yesterday. And the blocks right here, you see, tells you like the blocks in the set partition, right? The things that are connected. And it doesn't matter which graphs you choose. All that matters is connectivity and everything will work. And there is a product when you're doing diagram algebras of putting one diagram on top of another one. And when you're dealing with a partition algebra, it depends on this parameter n, which for us is coming from the Sn, right? This is the same n as in the group. And you get copies, you see, you get powers of n, and these correspond to these middle components that float in the middle. So you count how many things are floating in the middle, and that becomes the power of n that occurs. So this has been studied a lot, this algebra, since it was introduced by Jones and as a centralizer algebra, and it was introduced all simultaneously almost by Martin Pol, more in terms of diagrams. In terms of generalizations of the Potts model in physics, it has an identity, right? And it's because of the basis, it's set partitions, the dimension is the Bell number. If you don't know about this algebra and want to learn more, there is a very nice paper by Halverson and Ram, but Halverson has worked out all the character theory, like similar to, character tables for like finite groups. Jacobson and Halverson wrote like a very nice article, like, about the representation theory. So there is a lot of very beautiful resources out there if you want to learn about this. This is a very cool algebra, and it has like tons of like subalgebras, right? Including the temporal algebra that appeared yesterday. So now, we know a lot, like, so we know that the irreducible representation, well, the algebra is not always semi-simple. So if you take the parameters, so if you take the parameter n to be an integer between 0 and I think it's 2n minus 2 is not semi-simple, but for every other complex number, it is semi-simple. And when it is semi-simple, you actually, they are indexed by partitions of partitions that satisfy this condition. You can think of them as partitions of n. Similarly, as for the symmetric functions that we introduce, right, with an additional long row and then a partition lambda underneath, right? And then these parts have to be less than or equal to k. So every partition from the empty all the way to partitions of k will index an irreducible, right? The irreducible basis, is a standard tableau. And remember what I told you, standard before, you don't repeat numbers. So basically the entries form a set partition of k. So you can take a set partition of k and fill the boxes in all possible. You can leave, empty boxes, right, on the top, and Jones proved that the partition algebra and the symmetric group Sn, this is the same end there, form a centralizer pair. So basically, it completes this diagram, the seesaw pair right here, right? And remember what I was telling you, that I'm interested in the restriction problem right here, right? But now I can transfer it to a restriction problem right here, right? And the advantage is here is infinite dimensional, this is finite dimensional, so we were hoping that this would generate kind of more concrete, something to work with, more examples, right? So here is the same results, but now for the seesaw, right? If I want to restrict from here to here, I can restrict from here to here, and I will be getting the same multiplicities on both, right? So the idea that we had was to try to see if we could do this restriction, okay? Okay, so, well, the coefficients are the same, so we have to find a way to do this restriction, right? And one idea, right, that actually this was an idea of Nate Hartman. Actually, that's where we picked it up. But he was looking at the general linear group part, right? And he had the idea of restricting from GLN to some complex reflection group to SN, right? But we thought we would go the way of the diagram algebras way, right? And if you restrict from the partition algebra to somewhere in the middle, we thought, right? And then restrict from there. And choosing this part in the middle, right? That's kind of like the tricky part. So we want to choose some algebra right here. This is the algebra of uniform block permutations, which I will explain in the next few slides. So if you restrict from the partition algebra up to here, the coefficients that occurred are generalized Littlewood-Richardson coefficients. So that kind of is understood. So now from here is these special cases of Plethysm that I was telling you about. So the restriction coefficients. So, but why would you choose UK, right? Well, we wanted to choose something that is smaller, right? As you can see, that's the dimensions, right? And this algebra also has a lot more structure. It's a monoid algebra. So it and it's not only a monoid, but it's an inverse monoid. It's as close as you can get to a group without being a group. And you see, while the PKN, right, can be non-semi-simple, right? The UK is semi-simple always. So then it's kind of a good place to stop and see how this happens, okay? Uh-huh. An inverse monoid is a monoid where you can find an element. If you give me an element, I will find a tilde element that when I multiply them, I get an idempotent. Right? And basically, maybe I have to make a pitch for, Benjamin Steinberg wrote an amazing book on monoids. And if you want to learn about monoids, that's an amazing book. And he has a quote there that says that to think about monoids, think of having these lattice of idempotents. And basically, you have all these groups, right, that are kind of connected with this lattice of idempotence. So it's a very beautiful theory. So I really love that book. So you have, so this algebra, the uniform Black permutation, first occurred in the work of Tanabe, and then Kosuda took some limit. It occurred as centralizer algebras for complex reflection groups, and Kosuda called it the party algebra, because it reminded him of seat arrangements on tables or something like that. Anyways, but mathematically what they are, right, a set partition is uniform if every block, you see, if I look at every block, it has the same number of vertices on top as on the bottom, right? And they always propagate, like you don't have things that, set partitions that float only on the top or only on the bottom. But the nice thing is that when you multiply, it's a true monoid. There is no parameter. When we multiply in the partition algebra, you get this parameter. Here you don't get a parameter because it's a monoid algebra. So it's kind of a pretty nice algebra, right? So the idempotents, right? They are indexed by set partitions of K, right? So if you give me any set partition, I basically create like the diagram, right, or the set partition that has like the same bottom as the top, and connect them all like that, right? And we call the idempotent that has type lambda, partition type lambda, but by counting the sizes of the block. This has a size block 3, 2, 2, 1, 1, right? So 3, 2, 2, so that's the type of this partition. And so you have a complete set of, for every set partition, you get an idempotent. And when you are studying monoids, there are all these classes that helps you do everything, right? And one thing is that you have these J classes, right? And these J classes, you take one of the idempotents, it doesn't matter which, and you permute on top and you permute on the bottom in all possible ways. So here are the J classes for U3, right? And it so happens that UK is the union of J classes, like you kind of just taken by, which perhaps you can see, right, already. So in terms of so the first thing that we did in our work was study the representation theory. And what we wanted is to obtain a Tableau model for the representations, because we are interested in kind of generalizing these Tableau interpretations. So we found a complete set of, indexing now the partitions, the irreducible representations are indexed by sequences of partitions, right, that satisfy this condition right here. Here is an example for I3. The uniform Black permutations with 3 vertices on top and 3 vertices on the bottom has 5 irreducibles. These 3 right here are the irreducibles of the symmetric group. So the symmetric group is contained in U3, as we know, and then there are 2 others. And we also found, like a spanning set, right, for the irreducible representations. They are given by set fill, and the idea is that on the first, you fill them with just single numbers. On the next one, you fill them with pairs of numbers. On the third one, you fill them with third. That's what this uniform Tableau idea. They are standard in the sense that every number from 1 through K occurs exactly once, right, in one of the sets. So we have a complete, combinatorial way of describing the irreducible representations. So we also worked out quite explicit formulas for the characters in terms of subgroups that are young subgroups like this, right? So that here the formula doesn't matter, so don't worry. So the whole idea is that we were able to write the characters simply, as some multiplicities with characters of these young subgroups right here. And so here is kind of like a small example, like, here you are using just the characters of S2 to compute these ones. One thing that is, this is a very small example, but the coefficients here are actually integers. And we actually found an explicit formula that counting, these coefficients are actually always integers. And we have formulas, but I didn't want to put it up. So what is the connection to Plethysm, right? So now we want to restrict from the uniform black permutations to SK. That's what we wanted to understand. So we, in our paper, we have a Frobenius map, right, which connects to symmetric functions. And so here, the multiplicities, so when you restrict uniform black permutation representation to SK, right, the subgroup containing here, you get these multiplicities, and these multiplicities turn out to be products of Plethysms. So in the special case that you restrict representations that have only one partition and no other partitions, that you get this Plethysm, which is the one that we are interested. So if you restrict certain representations of UVP, you will get this. So then the question is, how do we do restriction or induction so that we get new information, right? So that we can compute this. So we were stuck on this for a while, like trying to figure out how to do, this. So the idea was that we are going to do this in steps, right, like to try to gather more data. And what we started to study are the sum monoids of the uniform black permutations that contain the symmetric group. So see what happens. And we discovered some things, that every submonoid that contains the symmetric group is also going to be the union of J classes, only certain J classes. So if you want a subgroup that contains a submonoid of UK that contains SK, it will be a union of some J classes. So then if you take the set of that contains M is a monoid, right, that contains, and you order them with inclusion, right, like one containing another, this, what we found, proved in our theorem is that this forms a distributed lattice. So here is an example, the very small example. Remember, these are all the J classes in U3, right? So if you construct, there are going to be only 3 submonoids, S3, right, which is a J class itself. You have this one in the middle, and then you have this one, and the containment goes this way. And in this case, well, this is the lattice that you get, but it's very small, right? Mike also kind of ran some programs, and enumerated like all the different, the number of submonoids that occurred, when you, for each K. Sorry, it went backwards. So here, so this led to a new order on partitions. So it's kind of very beautiful, like how, you are trying to understand these things, right? So we have a new order on partitions that do not contain the partition 1 to the K. And this order, right, so it goes 4, right, is smaller than 2, 2, and it's also smaller than 3, 1, and it's smaller than 2, 1, 1. And you can read this, but it's easier to see it here with this picture. So with that, this is the lattice of set partitions, right? And the definition says that if you can find set partitions of K, right, such that when you take their joint, right, the ones that you're taking all have the same type lambda, and you get type mu. So here is the example, right? So here is pi 0 in blue, right? Pi 1, and if you take their joint, right, it's going to be the set partition 1, 4, 2, 3. So that tells me that 2, 1, 1 is bigger than 2, 2. And if you, similarly for the red, right, these ones have type 2, 1, and this one has type 3, 1. So then it tells you that 2, 1, 1 is smaller than this. So anyways, so the theorem told us, right, so that if you, a union is missing right here as a typo. So if you have a monoid, right, of UK that contains SK, right, it's going to be the SK union, the union of J classes, where the J, right, is going to be an order ideal of this poset right here. Right? So for instance, for this one, we would get this now, right? Like these are all the possible submonoids, and it's a distributed lattice as we had before. We also, I'm running a bit of time, but in the paper, we have other poset properties of them, like, a characterization in terms of coarser. This SP means the smallest part greater than 1. In mu is greater than the smallest part greater, Anyways, so there are kind of all kinds of nice stuff. So here are more pictures. I'm kind of finished, and I want to also say that, in our work, we are in the process of understanding these restrictions, right? And how, doing the restrictions along these paths on these lattices, right? To try to see if this will give us new information. And we are finding in examples at the very least that is giving new information. So we are cautiously hopeful, because you cannot be too hopeful when you're working on such a hard problem. But we are having a lot of fun. So new combinatorics, right? There are interesting connections that I mentioned in the paper, like, for instance, for symmetric chain decompositions, we have also been working on that, which is connected to Plethysm, right? Because these coefficients, right, will tell you the number of starting points at a given level, right? That is giving you information about that. In symmetric chain decompositions, there was a paper by Folstis, Sternfels, and it's very studied. She's here, and Sternfels is here, and they found connections of UVP to algebraic varieties related to quantum chemistry. So there are all kinds of amazing connections, right? So, very exciting. So I want to thank, and I put everybody, because I've been, even when you're only part of, like, one of these, you still do a lot of work. So I'm very grateful. I've been in program chair, so I know how much work it involves. I've been in program committees. I've been organizing committees, and putting a conference of this size takes a lot of effort, as you can see by all the people. I didn't want to leave anybody behind, because I'm very equally grateful to everybody that has been involved with the conference. And thank you for having me here. I also want to put a plug for you to plan your next teaching year. We are going to have a special semester at ICERM on categorification and computations in algebraic combinatorics. You can go look at the list of people that have already agreed to come, and we are getting a lot of applications, right? Applications are open, so please, feel welcome to come. Providence is considered the second best, right after some Richmond, Virginia, in some list of nice small cities. It's a beautiful, beautiful city. Like, if you have not been, it's worth visiting ICERM. Like, the director there wants people to come.
Well,
anyways.
It is.
It is. I forgot, I couldn't find my pictures, like, from the window of the office. You want to be there. Anyways, Chris Bowman is here. I'm here if you have questions, or you can contact the other organizers. But, just Chris, if you have any questions, Chris. He's very good. Anyways, okay, so thank you so much.
All right, thank you, Rosa, for that fantastic talk. We have time for a couple of questions. If you have a question, raise your hand and we'll run a microphone over to you. So I'll get this one.
Yeah, thanks a lot for your very nice talk. And I would say I'm quite happy to see some monoid in FPSAC, because I feel they are not
Enough.
not sufficiently many. And I have a question related to that. So it's probably your. So you have this proposition that any submonoid of the uniform partition monoid, which contain the symmetry group, is a union of J classes.
Yes.
Is there a simple explanation for that? Why is there something like that?
Well, so as soon since it has to contain the symmetry group, right?
Yes.
And it has to contain a subset of the idempotents. As soon as you contain a single idempotent, it will have to contain the whole class because the symmetry group is in there.
Okay. Oh, I see.
Right? Because
So
you
okay.
multiply it on both sides, right? And you will generate all the elements of the. But it's something very special. Like there are not a lot of monoids where if you write all the submonoids, you will get like
it's
a distributed lattice. So we were kind of like very surprised that it turned out to be this pretty and that we were getting such beautiful pictures, right? So the numbers here are the sizes, and then kind of like the partitions that you're adding, like the idempotents that you're adding at each step.
Okay, thank you.
All right. Did we have another question up there?
Is it on now?
Yeah.
Thanks so much for the very nice talk. I had some questions about these posets. They look really cool. Do you have any information about the topology of these things, or the nice numbers that pop out?
Yeah. So, Mike, what did we find in terms of Cohen? We looked at some questions of the Cohen-Macaulay.
Partition. So it's very similar to the partition lattice on partitions, where you join parts, and that has very poor structure. Like Ziegler had an early paper that said, this is definitely not a well-behaved poset, and he gave some sub-posets which made it act terrible. And this one has also the same sub-posets. So we made those comments in the paper.
Oh, cool, thanks.
Sorry, on the same question line, I see from the pictures that this poset is not even ranked. Is that right?
It's not, yes, because you see here this one, right? Oh, sorry, this one, right?
Okay.
So if you go like that, right, then this one jumps up to here, right? Yeah.
Okay, so it's. Oh.
All right, I see there are many more questions, but we do have another talk at 10 o'clock. So we will have a coffee break at 10:30, at which time I would encourage you to talk to Rosa about these very interesting topics. So let's thank Rosa again for her talk.